at time t naught. And coincident to that idealization is this Dirac Delta function. But to me, the Dirac Delta function is more interesting in the sense that it allows me to do things like, if I say the Dirac Delta function, the three-dimensional Dirac Delta function would be, say, delta of x, delta of y, delta of z, right, where r is x, y, z. So with this three-dimensional Dirac Delta function, I can do things, right, like, say, the charge density of an electron with charge, or a point charge with charge q at position r naught, I just say q times delta function of r minus r naught. This gives me an actual straight-up formula for the charge density of a point charge. If I integrate that density over a volume, it's 0 unless something very special happens, unless the point r naught is within the volume. And that's what we mean by a concentration of charge at a point. The Dirac Delta function allows me to describe that somewhat carefully with somewhat uncareful mathematics. Well, I say that in jest. I mean, the rigorous mathematics to justify and prove the existence of the delta function was, I think, settled back in the 1930s or 40s by a mathematician named Schwartz, if I remember right. Something like that. Now, I think Dirac did these things back in the earlier, or like maybe 1920, 1910, somewhere in there. I'm not sure. Dirac was one of the founders of quantum mechanics, right? But he was also pretty careful mathematically. He knew the limitations of his physics. Okay, so you're like, well, that's great. Now the other thing, to give you a more, a less, what's the word? Let me give you a physics 1 kind of interpretation of the delta function. Is a hammer hitting a nail, or something like a hammer hitting something. So what's a hammer hit look like? If you take a hammer, or I don't know, you take this chair, right? And you like hit the ground with it. Like that, right? Something like that. It's happening over a brief period of time, right? And imagine that the whole chair was a giant hammer that I had brought to class, because I should have thought of that, but oh well. Anyway, so if you think about, or me just, see, if I do this, my hand's going to hurt the next day, but there. Sad. I should like, what you should do is I should get Dr. Sprano to come over here and like, I should just transport whatever, if I could bring the 200 class over here, have them do whatever sort of mathematical heresy they did today, and then, provoke the reaction, then he would, then you get the right kind of pounding that would be needed. But I'm not going to do that, because my hand is not going to hurt for the next day. All right, so the point is that the force is applied over a brief instant of time, right? And really, the only way you could measure that in some meaningful context is to measure the momentum which is transferred to the thing, right? If I was to say, take a ball, like a steel ball on a table, and I took a hammer and whacked it, I could measure the velocity after for the steel ball, right? And I could see how much momentum I had transferred from the hammer to the ball by just an explicit experiment, right? That transfer of momentum happens over milliseconds as the hammer hits the ball, right? Or you could think about, what's those tables with the, talking about the, what are these things called? Pinball, right? That's another thing. You have the little flappers, they hit the ball. That's a lot like this. Oh, wait a minute, no, that's not like this at all, because the ball gets on there, and sometimes if you get it right, you can have it roll along there and spin it. And not what I want. Go back to the hammer. So my larger point, though, is if we make a force time graph, right? The graph for a hammer hit is something like this, right? And if you don't care about the details of how much, what the delta t is, if this delta t doesn't really matter to you, you just know that the hammer hits at time t naught, then the force for a hammer hit would just be the impulse delivered, J, times delta of t minus t naught. See, because if you integrate f of t dt from, say, t1 to t2, you're just going to get j naught, provided that t1 is less than t naught is less than t2. Right? Over any duration, that's the impulse delivered by that force, which is a hammer. Right? So the Dirac delta function is also sometimes called the unit impulse function, because it gives an impulse of 1. All right, so finally, let's get to the math. The integral, what is the Laplace transform of, let's say, f of t times the Dirac delta function of t minus t naught. Integral from 0 to infinity, e to the minus st, f of t, delta of t minus t naught. What do we get? So the way this works is, assuming t naught is positive, we just evaluate, right? Dirac delta function turns integration into evaluation. We have e to the minus s t naught, f of t naught. So special case, the Laplace transform of the Dirac delta function of t minus a, let's say, it's just equal to e to the minus sa. So, you see people introduce this Dirac delta function. It looks kind of scary at the start, but I tell you what, if you have the choice to work a problem on an exam, and one of the problems has a unit step function, and the other problem has a delta function, you choose the delta function, because it makes life much easier. Let me show you. So example, if we're to solve y prime prime plus y equals to, let's see here, delta of t minus pi over 2. We did u of t minus pi over 2 earlier, didn't we? Right? We did. And we'll use the same initial conditions even. Y of 0 equals to 1, y prime of 0 equals to 0. So take the Laplace transform, we've got ourselves s squared big Y plus, minus s, right? Plus big Y equals to, what's the Laplace transform of delta of t minus pi over 2? It is e to the minus pi s over 2. And so we get s squared plus 1 times big Y is s plus e to the minus pi s over 2, which tells me then that big Y is equal to s over s squared plus 1 plus 1 over s squared plus 1 e to the minus pi s over 2. And then I can take the inverse Laplace transform. This one's simple enough, I can just do it in my head. Y of t is cosine t plus, now the Laplace transform of, inverse Laplace transform of 1 over s squared plus 1 is what? What transforms to 1 over s squared plus 1? Sine of t, right. So I use the Pac-Man equation and trade your sine t for sine of t minus pi over 2. And then the Pac-Man equation puts a unit step function t minus pi over 2 right there like that. And there you go, solved. Now I probably should do another example or two of these for you guys, and I'll probably do that next time, but with the time remaining, I want to project something for you. So I've shown you all of the main ingredients except for one here. And so pretty much all we have left to do for Laplace transforms is just put these things into practice, all right, and work some sort of more laborious, algebraically laborious problems, which we will do. Hopefully next class. Let's see here. Come on. Now, I would say, if you know you've got a lot of time pressure after this weekend, but you've got time to work on this course this weekend, a smart thing to do would be to go watch one of the Laplace transform lectures from a previous year, where I actually do the harder calculations that we're about to get into. So you'd be done with that, and then just saying you could work ahead if you know you're going to have time pressure from other things past this weekend. I don't know what your schedule looks like, but just a thought. Because I will post the next quiz here, hopefully by the end of business today. I mean, before I go to sleep today, hopefully. And then it'll be due, when is it due? Due on your birthday. Okay, well, you're welcome. So the next thing I should at least mention to you is convolution. And this is the definition of convolution. F convoluted with g is defined to be this integral, which is kind of mysterious. Here, for example, the convolution of t with t squared is 1/12 t to the 4th. Convolution is an interesting algebraic properties. You can easily show from the definition which I just gave that convolution is commutative. It has nice distributive properties. It's even associative. The convolution of 0 with the function 0. I mean, it's pretty nice, pretty nice. And that alone is kind of interesting, but the real reason we care about convolution is it trades convolution in the time domain becomes multiplication in the S domain. So convolution gives us a sort of product rule of sorts, kind of, for Laplace transforms. More to the point, if we wanted to calculate the inverse Laplace transform of F and big G, we can just calculate the convolution of little f and little g. Well, that's pretty fantastic, because the cost of doing this directly has been sometimes laborious, partial fractions decompositions. And there are certain things we don't know yet. Now, this is a proof of the convolution theorem. There's a typo that's unfortunate. This should be dv. Once you change that to dv, if you sort through this, it should make sense. And this is just showing you that the Laplace transform of the convolution works out to the product of the Laplace transforms of big F and big G. That's quite pretty. Here's an application. I mean, there's different applications you could make. One of the applications you could make would just be to find an integral solution. So if g is like, arbitrary function here, and I'll take initial conditions to be 0 for the sake of keeping things pretty, take the Laplace transform, little g becomes big G. We solve for big Y, we get that. And then the convolution theorem says that the inverse Laplace transform of this product of functions is the convolution of the inverse transforms, which means sine of t convoluted with g of t. But what is that? That's exactly an integral involving sine and g. So this would there'd be the same integral that you would have derived with variation of parameters in the other technique, truth be told. Here's another one. Here I look at a specific example with a cosine here. Building off the previous example, I calculate the convolution, out pops 1/2 t sine t. So it's another way of deriving. It's another way we could derive the t in like the repeated root case. This we had to earn with like the annihilator method before, because there's overlap between the homogeneous and the forcing term here. So convolution gives us another significant tool to analyze the general theoretical structure of non-homogeneous problems. I'll probably say more about that sometime, but that's the other tool. Now, Here's an explicit. I'm trying to find. Here's one. So if you were to calculate the inverse Laplace transform of 1 over a quartic, you could use convolution, and it works out to this. That's not something that's on your sheet, right? So convolution will take us past the sheet to harder things, but it's really test inappropriate because it involves integration, which I really don't expect you guys can do. So, but it is an important theoretical technique, which is why I'm talking about it right now. So now we've talked about it. Let's go about our day. Wait a minute. This is the weekend now, right? I don't see you guys again until when? Tuesday. That's right. All right. Thanks, guys.
Is there any chance you're going to have the next homework by Tuesday?
The next homework should be hopefully posted tonight.
Awesome.
Yeah, that's my plan.